Science has always been the realm of discovery and progression in the fields of medicine, biology, chemistry, space exploration, and so many other fields. The subject of chemistry has proven to be one of the most useful in its applications in areas such as medicine, electronics, the creation of the automobile, and so many other areas that have been important for the progression of human life and discovery. The reason chemistry and other fields of science work so well is because they utilize the scientific method and rely on evidence and data to obtain information about the natural world. The scientific method is usually started out by making an observation about a natural phenomenon and then forming a hypothesis, which is essentially just an educated guess for explaining that natural phenomenon. The next step is the experimentation stage, in which carefully thought out experiments are carried out in order to gather data and information that may support or not support the hypothesis. Whether the data does or does not support the original hypothesis is not necessarily what is most important about the stage in utilizing the scientific method. The data gathered actually allows the scientist to refine and fine-tune his hypothesis or come up with a new hypothesis altogether. So either the data works with the hypothesis or they have to go back, fine-tune it, or redo it. Once a hypothesis that is able to predict what the data will be is produced from the stage, then a scientific theory is created, which is a model for the natural world. The theories of gravity, evolution, the germ theory of disease, and all other theories were created from the scientific method. When gathering data, the data measurement should be precise and accurate. Precision is how close measurements in a series are to one another, as demonstrated here with this crude drawn dartboard. Accuracy is how close each measurement is to the actual value of what is being measured, as shown here. Precision and accuracy are both affected by systemic and random error in experiments. Systemic error is the error in measurements produced by flawed techniques, faulty equipment, mistakes, and all sorts of other problems that could arise due to our human nature. Random error is just error that will always occur and is just random. You cannot stop random error from occurring, and you cannot predict how much random error will occur. In order to build upon past knowledge of the natural world, it is important to know and understand the basics of the field in which you are studying. The most basic building blocks of chemistry are atoms, elements, and the chemical and physical interactions between these elements. Atoms, as shown here, are composed of positively charged protons, neutrally charged neutrons, and negatively charged electrons. The different combination of these subatomic particles create an atom of a certain element. For example, a hydrogen atom only has one electron and only one electron and one proton. So after many decades of experiments and discoveries, it was found that atoms are electrically neutral spherical entities that have a nucleus where all the positively charged protons reside with the neutrons and with the negatively charged electrons orbiting, as seen here. This combination of subatomic particles creates a certain element, and in most cases of the natural world, this combination is only that element. These atoms of certain substances are known as elements, such as the elements of hydrogen, lithium, iron, and so on. Each element is composed of only its respective atoms. Hydrogen is composed of hydrogen atoms, and iron is composed of iron atoms. The various combination of subatomic particles and the interactions of their electrons are what create the different physical and chemical properties in each element. Next comes compounds. Compounds are two or more elements that are chemically bonded together to form a new substance. The properties of compounds are usually very different from the properties of the individual elements that produce them. Lastly, there are mixtures, which consist of two or more elements and or compounds that are physically intermingled but not chemically combined, such as salt water or sugar in a cup of tea. Compounds are created either covalently or ionically. Due to the electrons orbiting the atoms and the attraction of electrons to the positive protons bonding to different elements occur. When an atom of one element loses one electron to another, the two form an ionic bond. When two atoms share an electron, then they form a covalently bonded compound. When an atom loses or gains an electron, it becomes an ion. An ion is an atom that no longer has a neutral charge. The loss of an electron from an atom forms a cation, and the gaining of an electron from another atom, it forms an anion.
The mole is a unit of measurement used to tell us the amount of a substance. It is represented by Avogadro's number, which is 6.022 times 10 to the 23rd atoms. So, therefore, 1 mole of a substance is equal to Avogadro's number of atoms. Knowing this is very helpful, as it tells us not only the amount of the substance, but it also tells us the mass of it, since the molar mass of a substance is equal to 1 mole. So to determine the number of moles, all you have to do is divide the given mass by the molar mass. For example, if you have 5 grams of carbon, you would just need to divide it by the molar mass, which is 12.01, because that's equal to 1 mole, and you would get 0.42 moles of carbon. And if you want to go a step further, you could figure out the number of atoms. So you would multiply the number of moles that you got from the previous equation, and multiply that by Avogadro's number, which is 6.022 times 10 to the 23rd atoms, and you would get 2.53 times 10 to the 23rd atoms of carbon. So here you have a molecule of sodium chloride, and this represents a molecule of water. Whenever sodium chloride is placed inside of water, the sodium separates from the chlorine, and they form individual bonds with water. An acid-base reaction involves an acid and a base reacting to produce water and a salt. Acid and bases are categorized by their ability to dissociate into ions in water. If they completely dissociate, they are considered to be strong acids or bases. Acids have 1 or more H ions as part of their structure, while the structure of a base contains either an OH atom or an O2 atom. In acid and base reactions, the acid acts as a proton donor, giving its proton to the base, which acts as a proton acceptor. Here you have HCl and NaOH. HCl acts as the acid, and NaOH acts as the base. When they react, they combine to they react to form water and NaCl, which is a salt.
The original ideal gas law is PV equals N times R times T, where P is pressure, V is volume, N is the number of moles of gas, R is a constant, and temperature is in kelvins. Recalling that N is equal to mass divided by molar mass, we can substitute here N, so we have M over, that should be capital M. So now we have this equation, and then we can rewrite this equation in terms of M over V, and if we recall, M over V, or mass divided by volume, is equal to density. So this reveals that density is equal to P times M over R times T. And what we learned from this is something pretty important. So this reveals that the density of a gas is directly proportional to its molar mass right here. Also, the density of a gas, density, is inversely proportional to the temperature. As we can see here, this is on the bottom, it's in the denominator. As the volume of a gas increases with temperature, the same mass occupies more space. So the density of the gas is lower. Each gas in a mixture of gases exerts a partial pressure equal to the pressure it would exert by itself. This is called Dalton's law of partial pressures. So the discovery by John Dalton is that in a mixture of unreacting gases, the total pressure is the sum of the partial pressures. So we can basically say P1 plus P2, the pressure of one gas, which you could calculate from this equation, plus the pressure of another gas, would equal the pressure of the two gases in a mixture. And they can be reacting, so that holds true when they're not reacting.
In 1913, Rutherford and Bohr introduced the Bohr model of the atom, which depicts a small central atom, a positively charged nucleus, surrounded by electrons that orbit in perfectly circular orbits. These orbits were called energy levels. And this model helped explain the Rydberg formula for hydrogen spectral emission lines. The Rutherford-Bohr model, while exceptional at providing insight at how the atom works, is kind of inaccurate. A more accurate version of the atomic model would be using the quantum mechanical model. The quantum mechanical model of the atom revises the Bohr model by saying that electrons are not exactly in circular orbits, but rather in a three-dimensional region around the nucleus called orbitals. The orbital can be defined as the probable location of an electron at any given time. The quantum mechanical model allows us to describe electrons using four numbers: n, l, m sub l, and m sub s. The first of these numbers, n, is based off of the Bohr model, which represents the energy level of the electron. The second number describes the shape of the orbital, so the dumbbell, the sphere, and then you get these more complex. Third number describes the orientation of the shape. So with the S, there's only one orientation because it's a perfect sphere. No matter how you orient it, it's going to be a sphere. You can rotate this into three different axes, and then this you can rotate and shift and morph and all that, and it just gets even more complex rotations and orientations. The fourth number, m sub s, describes the spin of the atom, which I'll describe a bit later. In 1925, an Austrian physicist by the name of Wolfgang Pauli formulated a principle stating that two identical particles that have a half integer spin cannot occupy the same quantum state simultaneously. This principle was called the Pauli's exclusion principle. For electrons, this means for a given atom, no two electrons can occupy the same four quantum numbers. Pauli's exclusion principle requires a fourth quantum number, m sub s, or spin, because two electrons can have the same n, l, and m sub l values in the same atom.
You said there are four quantum numbers, but that is only three.
Alright. The fourth number is the m sub s, which denotes spin. Particle spin is a type of angular momentum which has the SI unit similar to the normal angular momentum, kilogram meters squared per second. The quantum number representing spin is taking the SI value of spin and dividing it by the reduced Planck constant. For electrons, this cancels out all of the units and gives either a positive 1/2 or a negative 1/2 spin. This adds the fourth quantum number required to satisfy Pauli's exclusion principle.
Models of chemical bonding focuses on the three main types of bonds that hold elements together. We have ionic, covalent, and metallic bonds. An ionic bonding occurs when a non-metal transfers when a metal transfers an electron to a non-metal. Covalent occurs when the sharing of electrons between non-metals. In endothermic reactions and exothermic reactions are the two outcomes of compounds bonding. An endothermic reaction occurs when heat is absorbed as the net change of heat in the reaction between the bonds broken between the reactants and bonds formed between the products. And exothermic occurs when heat is released. And the Lewis structure utilizes a 2D structure to portray a compound's molecular formula as a visual model. Components that comprise the Lewis structure are the individual elements of the compound, as well as the bonds or double bonds or triple bonds that hold them together, and the electrons as dots. Our molecular shape and polarity determines the 3D representation of a compound as well as the physical properties. The molecular polarity is representative of the bonds that hold the compound together, and the strength of the bond in polarity determines physical features such as melting point.
A key concept of Chapter 11 is valence bond theory. VB theory is the overlap and bonding that occurs when adjacent orbitals' wave functions are in phase, which is very useful in determining molecular shapes. Hybrid orbitals can hold a maximum of 2 electrons. One will spin up and one will spin down. The distance between the nuclei determines the strength of the bond, and overlap is maximized to produce the greatest bond. The hybrid geometry depends on the constituent orbitals. These 6 types of hybrid orbitals are here. First, we start with the SP, the most simple, which is linear. Next is the SP2, a trigonal planar shape. Then is SP3 of tetrahedral shape. Next is SP3D with trigonal bipyramidal geometry. And finally, we end with SP3D2, which is octahedral.